Welcome back to the STA interview question series. So this is the chapter 2 of the series and we will be discussing about the timing arcs in circuits. Let us begin. So what are the different timing arcs in a circuit? You have the cell arcs and you have the net arcs. The cell arcs are basically the arcs inside the cells in your design, and the net arcs are usually the arcs that are connecting the two cells in your design. Let us discuss this in detail in our next slides. The next question is, what is uniqueness in a timing arc? We have three types of units. You have the positive unit, you have the negative unit, and you have a non-unit. A positive unit timing arc is if a rising edge in an input causes a rising edge in an output or no change in an output, it is called a positive unit. Or a falling edge in an input causes a falling edge on the output or no change on the output, it is called a positive unit. A negative unit is, as you imagine, is just the opposite. A rising edge on an input causes a falling edge on an output or a no change in the output. Or a falling edge on the input causes a rising edge on the output or no change on the output. It is called a negative unit. The third type is the non-unit. The non-unit is basically a change of output cannot be determined by change in input. So let us see the examples for all the different types. A good example for a positive and a negative unit is a buffer and a inverter. So what happens in a buffer? A rising edge in an input causes a rising edge in an output. So it's a positive unit. A falling edge causes a falling edge in the output. So it's a positive unit. Similarly, for an inverter, a rising edge causes a falling edge in the output, and a falling edge in the input causes a rising edge in the output. So it's a negative unit. Let us see other examples in the coming slides. So the next question is an AND gate a positive unit or a negative unit? Let us try to understand. So for instance, here you have a rising edge on a input A. Assume B is 1. Then you have a rising edge on a output. And assume B is 0. The output is no change. So it's a positive unit. Similarly, for the arc here, you have a rising edge on B. If A is kept constant or if A is kept 0, then you have no change. If A is kept to 1, then the output is a rising edge. So it's a positive unit. It's the same case for the falling edge. So you have a falling edge. If the output is no change, that is a be it as 0, then you had the output is constant. If B is 1, then you have a falling edge. It's the same for this arc. So AND gate is a positive unit. So in the last slide we saw an example of an AND gate which is a positive unit. Let us now see a NOR gate. So what happens in a NOR gate? When you have a rising edge in A, you have a falling edge in B if B is 0. Else if B is 1, the output remains unchanged. So it's a negative unit. It's the same logic for this arc. You have a rising edge, and if A is 0, you have a falling edge. If A is 1, there is a no change. So this is a negative unit. It's the same for a falling edge. For the falling edge, you have a rising edge if B is 0, and you have no change if B is 1. So your NOR gate is a negative unit. So AND and OR is a positive unit, and NAND and NOR is a negative unit. Let us see in the next slide what happens when we take the XOR example. So let us see the example for an XOR gate. So when there is a rising edge on A, when B is 0 you have a falling edge, and when B is 1 you have a rising edge. The same case for the B input, when you have B at 1, and when A is 0 you have a falling edge, and when A is 1 you have a rising edge. So what does this conclude? There is no clear relation between the input and output here. So XOR is a non-unit. It's the same case for the falling edge. For the falling edge you have a rising edge when B is 0 and falling edge when B is 1. So XOR gate is considered as a non-unit. Let us see where this unitness is used in STA. So in the previous slide we discussed the different unit concepts. We will try to see where this is used. The unit concept is used in the .lib file or the timing file. So if you open a .lib file for a buffer, you will see the timing sense, that is for A to Y, that is output, and the related pin is A. It is shown that it's a positive unit. Similarly, this is an AND gate example. Here you have a to Y, that is a pin which is a positive unit, and B to Y, as we saw for an AND gate, is also a positive unit. So in the previous slides we understood the concept of unitness. Now we will try to understand the different paths that are used for timing analysis. We have the data path, the clock path, the clock gating path, and the asynchronous path. I will show each of these in detail in the coming slides. So the next question is, what are the different data paths? The different data paths are, basically you have input port to a register, that is this path here. You have register to register, that is clock to Q. You have register to output path, that is from here to here. And you have a path from the input port to the output port. These are the different data paths. So what are the different clock paths? The different clock paths here is a clock path from here to from the input port to your clock pin. Basically there might be many buffers between the signals going from the input port to your clock pin. So here in this slide there are two clock paths. The next question is on the clock gating path. So many times in your design you may need to gate clocks to reduce dynamic power consumption. So here in the circuit you have this LD, which is a clock gating signal for this clock. LD is not part of any clock, but it is used for gating this clock. So it is used as a clock gating path. The last path is the asynchronous path. Here we see an asynchronous path from your reset pin to your reset of your flip-flop. So in today's lecture we discussed about the timing arcs and the different data paths. In the next lecture we will see how a setup and hold violation occurs and what are the equations to solve setup and hold problems. Thank you.